Hi everybody, I'm Randy, and I'm going to do this lecture, Template Metaprogramming. I'm turning into a junior over the course of this summer. Other than that, I don't have any cool accomplishments like Sean.
Yeah, Randy, you're just awful.
So here's a quick overview of everything I want to talk about. This is the coolest one, so I saved it for last. And I'll assume that you guys don't exactly know how to use templates and kind of ease into things for a little while, and then we'll get into other stuff. So the entire purpose of writing templates is to generate code for you. Writing code longhand based on what type you're using can be really slow, and then you have to duplicate it over and over again to incorporate different types into your code. So the whole point is just to save development time. And I think Professor Mead or somebody jokingly told me that templates were originally created so that the standard committee could make standard vector. Sweet. So even though that's what they're originally made for, they're used in a lot of other things that weren't their original intent. A couple of them are these two, metaprogramming and compiler reviews. We'll talk about both of those quite a bit in a moment. So this slide is just showing the annoyance of copying code a lot. Say you have a max function operating on integers. Well, that's cool, it works on ints. What if you want it to work on floats and so on and so forth? You have to copy and paste a lot of code, gets especially annoying here when you can have unlimited numbers of max overloads when you start using your own types. And this just demonstrates you need templates, otherwise you're going to spend all your time writing the same thing. There's one option, and it works in C as well. You can use token pasting to make your own functions, and you can pass in the type as a template, or not a template, a macro argument, token paste that onto the name of a function, and then generate and call functions like this. But there's a couple downsides that templates take care of. There's no IntelliSense. That makes it really hard to debug, and it's not very type safe because you're just token pasting everywhere. So especially if you're doing typecasting of pointers, there's no type safety involved in this at all. So then, instead of what I showed before, what's needed is a generic solution. That's what templates are for. There's the definition of templates from Wikipedia. I don't like that definition very much, so I'll just skip it. In short, a template is like an outline. It's not an actual function or an actual class, and it's not actual code. You create a template, and whenever you use it, code is generated as needed. And that's how templating works. Here's a pretty basic example, a generic array container. You can see here that it only holds 10 elements, and the 10 elements are of unspecified type T. So then whenever you create a new array, the templater, or the compiler, will create different versions of this class template based on the different types that you're using it with. Here's creating an integer array. So when this is first encountered, when the array of type T being replaced with int is encountered, the compiler will generate this version with int for you right then and there. And then that will be used from then on. So the whole point I'm trying to make right now is templates aren't really functions or classes. So if you try to take the address of one, that's not going to work unless it's an explicit instantiation of a template. You can't just be like address of that array. Like imagine it was a function instead of a struct. If you try to take an address of just a template, it doesn't exist anywhere yet, so you're going to run into errors there. And then, of course, when the compiler is instantiating all your templates, it's going to take time. Using templates increases compile time. And also, the last point that was kind of tricky when I first started using templates is that most implementation code, pretty much all of it, will go in a header file. Again, they're not actual. It's not actual code, so it doesn't go in a CPP file because you can't link to it. So everything goes in a header, so that way you can share the template through all the CPP files you need. So a quick thing before we move on is an explanation of the typename keyword. Compiler writers apparently were having a really tough time parsing C++. So they decided, hey, this stuff is really, really, really impossible to parse from a compiler-writer perspective. So what we're going to do is we're going to put some of the job in the hands of programmers. Whenever you specify some sort of templated type inside of a template, you have to say Typename. That way the compiler can tell that it's a type of something and not a variable. Because whenever you come across a name like this with these scope resolution operators, it's just assumed that it's referencing a member variable. However, if you specify Typename before that, then it gets cleared up and you won't have any compiler errors like you'll see in the next slide. Some compiler errors associated with this. So this is the example that I saw when I first learned how to use this keyword. Say we have here, inside of some structure, there's a member called, I guess it's called member, but it's an actual data member. And then the next one, it's a type def, but it has the same name. So then if you try to access it, like so, here inside of this function, some struct member is going to need to be treated as like an actual variable in order to print it out. So this line here will work. But if you try to pass in the type def version, then you're going to have some troubles. And I'll go on the next slide. There's some more details. Yeah, you're going to have some really ugly errors that aren't going to make a whole lot of sense. And you're not really going to know why. Even if you try to actually use it like a type, you're just going to be like, yeah, it's bad. Anyways, next slide. So what you do is you stick Typename in front of member. This should actually be type def. Typo there. But now that you said Typename, the compiler will know this is a type, not a member or a data member. And it won't freak out. And then you're going to have your code run how you expected it to. And you can actually use this as a type to make variables like the variable m, for example. Template specialization. So now that we're comfortable writing templates, sometimes just having a single generic template isn't quite enough. You have to actually write some special code for certain types. Template specialization lets you do that. Actual specializations are actual functions, so they go in a CPP file. They're not templates. A good example of template specialization would be standard vector. It's specialized for bool, so if you make a vector of bools, it packs them all together in memory. Usually a bool will probably just be 4 byte aligned if you just use one on the stack, but in a vector, they're not. They're all packed together. So here's an example of specialization of a print function. Here's the generic one. Almost every type passed in here will call this function. It'll say I'm not special. So then if you specialize it for a specific type, in this case int, here's what the syntax looks like. You still type the template keyword out in your type name. You don't have any type names or classes in here. It's just empty. And you specify your template parameter explicitly. So this is the syntax of creating a template specialization. So if you call print with either of these two, next slide, you can see that both of those are not special at all. However, the last one is pretty special because it has a specialization and it says so. All right, so here's a quick quiz. Which one of these compiles? I'll give you a moment to soak this in. All right, enough soaking. Next slide. The bottom one, and the reason for that is because this here is a template. It's not an actual function. This one is an explicit function with an explicit type, and you can take the address of it properly, and that'll work. So now let's move on to partial specialization. It's kind of like specialization, except the result that you write is still a template. And it's useful when you have more than one template parameter. You want to explicitly explicitly state that one of these is a type, and you're going to write special code for it. I don't think I explained that very well, and I didn't think I would, so that's why I wrote one more slide after this one. In the previous one, we just did for comparing keys inside of a hash node, perhaps in like a hash table or something. When you compare keys, usually you can just use the equal operator. However, in this case, we're going to specialize the first parameter here as a character pointer. And if you don't want to be like STL and just hash the address of the character pointer, you want to actually hash the characters, then you have to do a specific code for this type. And in this case, just calling strcomp. So specific code for one specific type, partial template specialization. That's a pretty good example. There's some other ones. This isn't actually used very often. Usually just specialization is enough, but it's occasionally quite useful. So one thing you'll probably want to do is, let's see, what am I trying to say here?
Cast function.
Let's just go to the next slide. Yes. So I'm trying to explain here that you can't partially specialize a function. You can in C++11, but I don't think any compilers support it yet. And if you try to partially specialize a function, you'll get pretty nasty compiler errors. So then what you do is you can only specialize structs. So instead, you'll stick your function in a struct. Next slide. So the whole point of not supporting partial specialization of functions, like the argument for not doing that originally was you can just use function overloading instead, and that'll work just fine. But as we saw in the previous slide, for example, when you need to compare strings differently than another type, you actually do need to specialize your code to be slightly different. So sometimes just overloading your functions isn't enough, and you actually do need to specialize just a function. So then in the next slide, I'll be showing template. Yeah, this is just an example of where function overloading isn't quite enough. Here in the first line, this is just like a general conversion function using just like a C-style cast right there with u. Converts type T to u and then returns it. But if you try to convert a character pointer to a double, then you're probably not going to be able to just type cast like that because crazy things will happen that you don't really want. So then you have to do something more than just function overloading. So first things first, stick your function in a struct and make it static. Static function in a struct or a class is pretty much the same thing as a global function, except the structure or class name is treated as a namespace. So it's like an annoying workaround that you have to do to partially specialize a function, but something you have to live with. So now this compiles, but it still doesn't work. Like that character pointer is going to be casted to a double, and then your double is going to represent some address. So then the next slide shows how to actually partially specialize a global function by sticking it in a struct as a workaround. In this case, I just called atoy, a2i, to convert the string to an integer, and then I typecasted that to a double. And if you call it, that'll work. This is what will happen. 37 converted to a double will be 37.0. And there we go. Good example. OK, next thing up is something called CRTP. CRTP stands for Curiously Recurring Template Pattern. The story is, in the past, people were doing this a lot in their CPP code, and there was no name for it. So then comes along some guy named Jim Coplian comes along and decides to give it a name, and he picks this one. So now that's what it's called. And it's useful for these things. Magic, template mixins, and static polymorphism. And we'll go over all three of these. I'm actually not sure if we'll do that one, though. So the first one is static polymorphism. Normal polymorphism is just using virtual calls to pick functions at runtime. You can do it during compile time as well. And here's an example of doing that. So the idea is you have some structure, just a normal struct. Ignore this part here for now. It has a function. And what you do is you inherit from a templated base and you pass yourself into the base parameter. That's how CRTP works. So now your base inside of your class has the type of the inherited type, and you can actually typecast to whatever you was inheriting from base and call things on it. And this will be compiled away during runtime. So then here's an example here. Making sum struct. This is all happening during compile time. And then you can call the base function, which calls the function on the derived type. It's kind of a roundabout way of doing it, but you avoid a dynamic dispatch, and it's a little bit faster. Here's an actual example of something that is slightly useful. You can make a couple different animals that roar, or actually they don't both roar, they just talk, I guess. Anyways, you can make a couple of them and then call the same function on both, and different things will happen.
Wait, what?
And this will be all happening, or all like, this will all be organized during compile time.
Wait, can you go back?
Yeah, okay.
You call
Stay here
L.interface
for a moment.
and L.interface, and it calls two different functions. Wait, what is it? Wait, how?
So I'll run through it real quick.
Yeah.
Whoa, this one, yeah. So we call L.interface, and this should be K.interface.
Yeah, okay. I was like, what just happened? That was
I told you there was magic. No, as a typo.
So is the only use for it is like it's faster than the virtual code?
Yeah, it's faster, and sometimes it can be used to keep the amount of code you have to write a little bit minimal. For example, here. Actually, this isn't the best example of keeping code minimal, but you can research that like
But this
afterwards.
is faster than the virtual code.
Next slide. Yes. So I went ahead and screenshot some of the assembly. This is using just like a normal virtual call. You can see there's I think this is a load effective address, and then a move and a call. So this is like push jump call, I think, is what I usually see, but for some reason I got something a little different. And then this is what a normal function call will be, just to like a function, push call, really short. One more instruction, a little longer. And that's the difference between a virtual dynamic dispatch function and a normal one.
That's crazy.
So that is called a mix. Well, I don't know if that's called a mixin. That was just CRTP before. So using CRTP, you can do something called make something called mixins, and that's where you can create a class and then inherit from different stuff. And each of one of those things you inherit from adds a little bit of functionality. So you're like mixing in functionality to make something else. That's the idea going on here. And this saves a bunch of time, because then you can just make little pockets of functionality and just stick them on other classes as base types. So a good example, this is my favorite one, is creating a singly linked list of everything of a specific type while it's constructed. So every time something is constructed that inherits from this, it'll be pushed onto a singly linked list. And then you can access that through a static function called head. So you'll type your type : head, and then that'll get a pointer to the first instance in that linked list. I won't go through exactly how this works. You can look at this later and analyze it.
Is this straight out of your reflection library?
Yeah, I was using this in my reflection library. So real quick, good example use is you have a bunch of global objects doing something when your program starts. Like their constructor will run some code. And then later on, you need to loop through and do something to all those globals. If they're all linked together in a singly linked list by this thing, then it's really simple. Simple to do that.
Why you can respond to more?
Can you say that again?
Go back one. Why on the head is reposing after it becomes pointed to
Here?
down there?
Oh, you set the head to null, and then you push into the, what is it called? Singly linked list. Every single time another one is constructed, so that null will always be at the end of the list, and it signifies the end.
Okay.
And then here's an example of actually doing that. Using these things can be really easy, so that's why they're really useful. Say we mix in this constructor lister into our sum struct. We create a couple of them on the stack or wherever, it doesn't matter. And then after we create them, you can loop over them with a really intuitive for loop. And it just works. It's pretty cool. So another example of a good mixin that I actually use as well is to make things a singleton. There's actually a little bit more to like these functions down below I couldn't put in the slide. But the idea is that you mix this into your class and then you can retrieve an instance with this get function. And then that's the only way that you can construct it with that get function because everything else is private. So if you try to construct an instance of the derived type, you'll run into the base type trying to be constructed as well, which is protected and you can't access it.
Wait, it's supposed to be private or protected? Because if it's a protected constructor, can't the deriving class still call that?
So the question was, should it be protected or private? Both ways, somebody that doesn't have access to the private data of your derived class can't call the constructor.
Oh, yeah, I see what you're saying. Right.
Okay, so let's move on to another topic. Metaprogramming. So the idea here is to utilize the compiler to do stuff during compile time. That way you don't have to do it during runtime. This is really useful for, I have 3 examples here, calculating things at compile time, generating some code, and having really flexible templates. So the way it works is you can actually, inside of a struct or a class, create a static const or an enumeration value and assign it right then and there during a template at compile time. So that means you can also do like math stuff on this value and then assign it right then and there. Older versions of C++, I believe, had to use only enumerations for this, but nowadays you can just do static const and then an integral type like bool and unsigned and so on. So in this case, our struct will be testing to see whether the integer passed in as a template parameter is even or odd. So go ahead and go to the next slide. You can see here that I just took a screenshot of my IntelliSense. Is even 10, I moused over value, and then you can see that value is true. So this did this thing at compile time. Here's another example, computing the factorial of something during compile time. This makes use of recursively instantiating the template inside of itself. So the way it works is, could you go to the next one? Right here, in this example, I pass in 16 as the parameter to factorial. So I is going to originally be 16. So you assign an enumeration value to I, which is 16, and then multiply it by the result of another factorial instance with 1 less than that. E is supposed to be result. It's probably a copy-paste error. So that should be : result, or result should be E, either way. So there's a recursive instantiation going on here where you multiply the previous by 1 less than the next over and over. And of course, you have to specialize the last one to not do anything recursively, the last one being 1, to where you just do your result as 1. That way you don't run into a compile error. Because if you only had the first one, you're just going to infinitely decrement I over and over and over again, and you don't have a way to stop. And then you'll have a pretty strange compiler error there. So anyway, 16 was the biggest number I could do, and you can see here as proof that it was calculated at compile time. So here's a few more ideas of things you can do at compile time. You can do compile time string hashing. It's a little easier with some C++11 features, but there's one way to do it in C++03, and I think I actually show it in another slide. You can calculate coefficients for binomials, or maybe it was powers, I can't remember. But if you have a long binomial that you need to calculate, for example, using Bezier curves, if you can make a Pascal's triangle at compile time, then you can have an unlimited amount of, I think they're called nodes, in your Bezier curve. You can also do a lot of shenanigans. You can make a cool static assert and compile time linked lists. This is a pretty crazy one I have a video on. I don't actually have slides on it though. Okay, so let's do a couple of them. This one is hashing strings at compile time. This is how you do it. In C++03, you have to separate each letter out and pass it in as a template parameter. So then what you do is you just have some sort of hash function that operates on your characters that you pass in. And then if you wanted this to support any size string, you have to make a lot of overloads. That's just the reality of it. Is that actually useful? Probably not, but it's still pretty cool.
What is the hexadecimal value?
That hexadecimal value, random number, and it's probably not a very good hash function because I just typed it out, like right then and there. Here's another pretty cool one. We can count the amount of stars on this gigantic pointer by hand, or we could make the compiler do it. And here's how you could do that. So you pass in an integer pointer into this struct called star counter, and it will recursively add 1 to value and strip off this pointer here using specialization, and the last one will be a value of 0. So then when you pass it in, you're going to count how many stars there are, take 1 off each time you count, and stop at 0. And then I think I have another slide. Yep, showing you that it works. There's 19. I didn't have to do that myself. I made the compiler do it. Here's static assert. So there's assert that you can use during runtime, and then there's one you can do that will stop compilation if something equals false. Let's see. Here is what it is when you pass in anything but true. It's not an actual struct. It's just a declaration of a struct. So if you try to instantiate one of these things, there's no brackets, so you'll have a compiler error. However, if your template parameter is true, then you can totally make one of these and you won't have any compiler errors. So you can use that to pass in a comparison into the static assert struct anywhere in your code, even just like out in the middle of your global scope. And if your comparison is false, you'll get a compiler error, and it'll say something that doesn't make sense, but it'll still have static assert in the name somewhere, so you can kind of figure it out. And if it's true, then your code will just compile and it'll work. And then I tried to make the error message a little nicer by using like line numbers and stuff and token pasting, but that's a little extraneous. You don't actually have to do that. Here's usage of it. There we go. This right here, 2 = 2, that's true, of course, so the compiler is quite happy compiling this. And if it's false, then you're going to have a compiler error. The compiler error is going to be pretty ambiguous. But the key thing is, next slide, you can see that the name static assert is in this error, and you can figure it out pretty quick. I also underlined the condition to make it clear. So the next topic is expression templates. So what is an expression? In a mathematical sense, it's a few different operations you perform on some operands, like that, a plus b minus c. So using an expression template, you can sort of treat an expression, like the general notion of an expression, as a type, an actual C++ type. So why would that be useful is the first thing I wondered when I started researching this. Here's a quick example of not an expression template. It's just an expression. If this code were to actually be run, a plus b minus c would be run, and then the result of that would be passed to this function. So if I was perhaps a really new programmer to C, I would maybe want that expression to have actually been passed in that function, but there's not really a way to do that. So
you mean like actual, just the act of a plus b minus c being passed as a function?
yeah, so here's just, I'll clarify real quick. I was trying to talk about the act of passing a plus b minus c into that function and how there's not really a way to do that. At least not one when you first think about it. So it would be nice if we could do this, make an expression a type, because say we have some arrays here and we want to do that expression on these arrays. This code totally wouldn't compile, but it would be pretty sweet if every element of A, B, and C one by one went through this transformation and actually assigned each result back into A. You can make a for loop to do this, of course, and just do it one by one on each element. But is that really as readable as that? It would be cool to do something more like this. Here's how you do it in like with the more conventional method using a function pointer. You can make a small function to represent your expression, and then you can call it inside of perhaps something like transform or standard transform, to where you just call that function and pass in your operands, and it'll work. However, this requires a jump in memory to call this function. And if you look at this, we're typing out the expression like in our code, and it will be known during compile time. So if you think about it like that, like this is known at compile time. So perhaps there should be a way to get this expression into this transform and use it during compile time as well. Because everything we need to know is right here. So it turns out that you can do this. Next slide. So yes, that's not ideal. This is just going over pretty much what I said in the last slide, so we'll skip it. I don't actually have any example implementation because I've never done it myself. However, Boost Spirit is a library created, and it's a library in Boost, I believe. And it's used to do a whole lot of stuff like I just showed. And you can go study it on your own if you like. However, it's a little bit outdated, at least in my opinion, because one of the points of using an expression template is to avoid copying temporaries around a lot. You can use R-value references in C++11 and move semantics to avoid a lot of that. You can also make lambdas, functions like there on the spot. And expression templates were also used as like an ad hoc replacement for these when they didn't exist. Anyways.
What's like some syntax you would be able to write like with expression templates?
You should probably just go look that up. Okay, moving on. So this is something Sean Middleditch taught me a couple days ago. There's an idea that you can use a template type simply as an arbitrary description of something. For example, here we can create a structure, and its name is quite descriptive, input iterator tag, but the actual definition is pretty meaningless. And you can use this to manipulate how a template acts. So this right here would be describing an iterator that does some sort of input. So the idea is that you can use a tag, a type like this as a tag to pass into a template, and it'll perform either function overloading or template specialization, and then do different things depending on what tag you pass in. And the actual meaning, like I said, is quite arbitrary, or the actual definition is arbitrary. Forget it, next slide. So the only thing that I've been able to see as quite useful for this in the small amount of time I researched it was for making iterators, and it's really cool actually. Here's a couple different categories of iterators that you might have. You might have some that can perform random access in the container, like an array. Others that can go forward and backwards, perhaps like a doubly linked list. And perhaps you have a default iterator that can only go forward. Perhaps if you're using a singly linked list, this would make sense. Here's a quick example of a generic algorithm operating on an iterator, and the iterator is passed in as a template type. And all it does is it advances the iterator forward by n. And if you pass in just any iterator here currently, it'll just do ++ on the iterator, and it'll be quite slow, an O of n operation. But we know that with perhaps a random access iterator, we can just jump there like that. So we need a way of doing that that makes sense. I'll go ahead and show an example of using function overloading. So instead of just doing an implementation inside of advanced, you have another layer of indirection, advanced implementation, and you pass in an instance of the tag itself into this impl. And tag here, it's important to note that this is a typedef type inside of this class. So inside of each iterator, you'll have a typedef of this tag type. And then you can create an instance of it right then and there and then pass it into this implementation. And then the next slide, you'll see function overloading is used to determine which one will be called. So here, if the type def inside of your iterator is just default, this is the function that will be used when you call advance. If it, however, has the tag of random access, this is the function that will be called, and it's quite a bit more optimal. And you don't have to worry about which one will be called when you're just using this function. All of this is just figured out internally in a really simple way. Yeah. OK, this is the last topic I think I have, and it's the coolest one. And it's called SFINAE, and it stands for Substitution Failure is Not an Error, which is a pretty abstract name. But if you bear with me, it'll make sense in a moment. So here is my definition that I wrote of how I think about this. The idea is, if you have overloaded functions and you call one of them, the rest of them can fail, like compiler fail, and it won't matter as long as one of them works. And the reason for this is because if you have a bunch of overloaded functions and you pass in a type to it, and some of those overloaded functions would crash, that would suck, because then you'd have to make sure every overload works for every type you ever pass into it. And that kind of just defeats the purpose of writing overloads in the first place. So that's why SFINAE exists. Here's a good example of like general, like standard use of SFINAE. We have two overloads of f, the function f here, both take in a template parameter type of t. The first one is accessing foo inside of t. Here you can see there's an actual type of foo, so that makes sense. It's an int. So this is just expecting an int of type def foo inside of t. However, the bottom one doesn't. It's just taking t itself as a type. So if you call the first one and you pass in this structure as the template parameter, overload resolution will determine that this is the best fit here. However, if you pass in just an int, overload resolution will stop here, see that that doesn't make any sense whatsoever. If this is the only function, this overload didn't exist, you'd have a compiler error. However, there's another overload, so instead of just compiler erroring and stopping, it moves on and sees if any of the other ones are valid. If it finds a valid function, then you can call it without any error, and that's that. So cool, great, overloading works, but this is C++ and we do things that people didn't intend for fun and for really cool, really awesome stuff that helps a lot. So SFINAE was originally used for overloading, but we can use it for runtime checking of Boolean conditions. And not only that, we can do different things depending on what those conditions are. And we can make the compiler check those conditions during runtime as well. So here's a quick few examples of what you can do check for with SFINAE. You can check to see if a class or struct has a member of a certain name. You can also see if it has a function definition inside of it somewhere. And it's pretty much in general, can this type do this? Yes or no? Next slide. So all these checks are really useful for these couple points. Avoid code duplication and make decisions during compile time. Anyways, let's move on to a real world example. Try not to worry at all about how SFINAE works. Just treat it as a black box for now. So a real world example that I actually used that was really cool is in my reflection. So real quick, this is what reflection is. It lets you do these things. They're really cool. This is how, generally, something like this, you'll register one of your types inside of your reflection. You can see here I'm registering this type, and then here's some information about that type. Next slide. One of the useful things that you can do with your reflection is to create, do factory registration or create factories for your types. One reason this would be useful is to create a type based off of a string. So I just want to create type from a string, which is really useful, especially if you're working with scripting languages. And the idea is that this right here line of code would return a pointer of a constructed type. And the way it works is you'll have a map of characters to creation functions. And this is the simplest version of a creation function that exists. Default constructor of your type, return it with new. However, there's a bit of evil in here. So if you zoom in, you can see it. That's a default constructor. What if your type doesn't have a default constructor? Well, your code will compile, or your compiler will have an error and your code won't work. Oh, dang it. So what you do is you use SFINAE to make a decision based off if you can just default construct this object. That way you can make sure your code at least doesn't just not compile. So there's two solutions. The one I just said like a moment ago, or you could just suck it up and deal with it. I did that, and you probably don't want to. You'll probably want to actually get around a problem like this if it occurs. So the solution that I think would be ideal in this situation is you can call create on a type that can't be constructed, but it'll just return a null pointer. Even better, you can stick in an assertion in this function, and not only does it return a null pointer for release mode, but it'll assert during runtime during debug mode. Hey, don't default construct this type, it can't. So this is what registration looks like, sort of. This is pseudocode. So here, we're registering type and its creator somehow. And what happens on the inside is we give this struct creation a type, and then it checks to see if it can default construct that type. And if it can, then great. Then we'll give it a create function, and it'll call new, and it'll work. But if it can't be default constructed, we'll give it this function here, which will just return null and assert. So that was the idea of how it works. So there's some good benefits with this. No compiler errors whatsoever, no runtime overhead involved, no additional complexity to the registration. When you use this reflection, it's not any more complex. You don't even have to know what's going on underneath. That's the biggest benefit. And then you can also put an assertion if you try to default construct something that doesn't have a default constructor. So then there's also additional error checking involved. There's only a couple downsides. It'll increase your compile time a little bit. It probably won't be noticeable at all. And it can be quite complex and weird looking, so that if somebody looks through your code, they're gonna be like, oh my God. So let's hit the ground running and just look at it. Here's a SFINAE check I created to see if something has a default constructor. It's important to note that the new standard of C++ has standard is default constructible. So you don't have to write this one specifically, but we're just going over the idea of how it works. OK, next slide. So you might have noticed the usage of this thing called decal type. It's a C++ 11 feature, and you should probably use it because it makes writing SFINAE quite a bit easier than if you didn't use it. And it just returns the type of an expression. So the best example that I could think of is right here. You have a function, and it has a return value. And say you need to create an instance of the type of its return value, but you don't remember or you don't care about what the explicit type is. Perhaps it's templated and it's like this long. You don't want to write that out. You can use decal type. This will determine the type of this expression, which will be the return type of that function, and you can create a variable like that, of that type. So here's a stripped down version of this has default constructor SFINAE check. So let's run through this real quick if we pass a type into it. Type goes into T. T goes into the SFINAE call, which is just a templated function. And there's those the ... operator there. That'll just catch any parameter that you ever pass in, like any type of T. That function will always compile. So then what this is doing right now is if you pass in a type, this will compile right here. This instantiation of SFINAE will compile. The return value is an int8, which is just my type def of character I use. And then you check the return value size, which is going to be the size of a character, and you see if it equals the size of a normal int, and that'll always be false. So if you passed in something in for the parameter here and you checked the value, it'll just always be false. OK, moving on. If you understood that, then this will make quite a bit more sense. Now we have two functions. The top one is the new one right here. This one has a different return value than this one. This one is an int 32, which is 4 bytes. This is a character. int 8, which is 8 bytes, or 1 byte, 8 bits. So now if you pass a type in, what will happen is the first thing that's checked is to see if it can be default constructed right here. It'll actually just like call the default constructor. It won't actually be running the default constructor because remember this is at compile time. But if it has the default constructor, this will not fail to compile. And what you do is you, oh wait, that's on the next slide. So that won't fail to compile, and the return value of SFINAE here will be the same as the size of an int 32, and then the result will be true. Okay, so the last detail is that star that I almost talked about a moment ago. That star confused me quite a bit when I was looking at SFINAE originally. The explanation that I understood and made sense to me was when you're dealing with SFINAE checks, it will only really work if you're using really simple types to pass in as arguments, like ints and pointers and so on. So putting a star there will just make a pointer to the type that's passed in, and that'll be the end of it.
Just real quick, the reason for the star is actually we're doing the overload of the triple dots right there. The triple dots, the ellipsis will only accept simple types. So if we're using this triple dots explicitly, any other SFINAE, it doesn't care about the pointers.
Gotcha. Okay, so he clarified, he being Sean right here. If we go back a slide, right here. Okay, so these triple dots only accept simple types, for example, pointers. So if you're using this syntax here with these triple dots as your catch-all, then you're going to need that star there, otherwise it's not going to work as intended. Okay, now I'm just showing that if you pass in a type that can default construct, that value will be true, and it'll be false if it can't. So now that whole ugly thing is dealt with, we can actually use it to make some sort of decision at compile time. This is what I'm actually using in my code, or something like this. This is making use of partial template specialization. And the way it works is there's a template parameter for bool, and there's a template specialization for true of that bool. So if you pass in false, you're going to get, if you call this getFunc function, null. If it's true, when you call that getFunc function right here, it'll actually return something, and I'll explain that in a moment. So I'm using specialization to either return one thing or another, depending on if I passed in true or false. Can you go back one more? Thanks. Okay, so that last one is something I haven't described yet. When you pass in something as a template parameter, if it's an integral type, then you can pass it in as not a variable, but like an actual number. For example, this is useful if you want to make a templated array with a specific length. You can pass in like 7 as the length, and that'll be an integral constant of 7 in your template. In this case, func is a function pointer, which is a pointer and an integral type. So you can use it as a constant here. Anyways, I guess I probably shouldn't have explained that because it's getting quite complex. Next slide. This is making use of SFINAE to either return null or a function pointer, which is what I was trying to describe last slide. I had to squeeze this into 3 different lines because it was really long, and it's really long in my code as well. But the whole point is now when we're calling this register here to register a function in our creation, to register a creation function in our factory, we can actually just give it a null pointer or an actual function that will return a new object. And which one of those is picked during compile time. And the nicest thing is all that crazy implementation is just hidden away in some file, and whoever's using this code doesn't actually have to oversee it. Okay, so this brings us to the end of the lecture. There's a few references that I learned from myself that I would like to recommend. First one is this book by Andrei Alexandrescu called Modern C++ Design. It's a really bad book name because it's not Modern C++ Design, but it has a lot of cool information in it. There's another resource here. It's actually a video that I have on my flash drive right now, And I think it's a little too big to fit on Moodle, so I can't. But it talks about template metaprogramming and reflection by a guy named John Edwards that did a talk here, and he works at that game company right now. And of course, there's some DigiPen student blogs that talk about some of this stuff too. And you can always email me. Is there any questions? Yes?
Double type is available on Visual Studio 2010 or until Visual Studio 2012?
Decal type is available on both 10 and 12. Yep. Oh, another good keyword is auto, also available on 10.
Which one?
Auto.
Oh yeah, I know about auto.
Cool.
Really useful.
All right, that concludes the presentation.